Hello everyone, welcome to my channel Physics for Engineers. I am Dr. Tirumala Rao Gurugubelli, Associate Professor and Head, Department of Basic Sciences, School of Sciences and Humanities, SR University, Warangal, Telangana, India. Today, we will be discussing about the classification of solid materials into three categories: conductors, semiconductors, and insulators. Particularly, we will be focusing on the properties, electrical properties, and electronic band structure of these materials. And then we will discuss about the semiconductors and their classification. Once again, I welcome you to the course. Have a wonderful learning journey with Physics for Engineers. Now that we have introduced the semiconductors, let us first understand how materials are classified based on their electrical behavior. In nature, the materials can generally be divided into three groups: conductors, semiconductors, and insulators. The conductors are the materials through which the electricity can flow very easily. I can give some examples like the conventional copper, aluminum, silver, and gold. These are the metals which can process the high electrical conductivity. In these materials, the electrons can move freely when the electric field is applied. This is why the copper is commonly used in electric wiring. At the other extreme, we have insulators. Examples: glass, rubber, plastic, ceramics, and dry wood. So in these materials, the electrons are tightly bound to the atoms and they cannot move freely. So the electrical conductivity is very difficult in insulating materials. Therefore, the current flow is extremely limited in insulators. Between these two categories lies semiconductors. Semiconductors conductivity is between the conductors and insulators. It is higher than the insulators and lower than the conductors. The most common semiconducting materials are silicon and germanium, which are available freely in the nature. So that these two semiconductors are also known as intrinsic semiconductors. What makes the semiconductor special is that the conductivity can be controlled by changing temperature or adding impurities or by applying external electric field. We can control the conductivity of these semiconductors. We can increase or decrease their conductivity. This controllable conductivity is the reason why the semiconductors became the foundation of the modern electronics. Every smartphone, laptop, computer, like computer processors or chips, memory chips, LEDs, solar cells, and communication devices that relies on these semiconductor materials. From the energy band perspective, the materials again classified as the overlapping of valency band and conduction band refers to the conductors, whereas in insulators, the band gap is very large. The conduction band and valency band are separated with a large forbidden gap. Whereas in semiconductors, the small energy band gap is approximately 1 electron volt. The small energy gap allows electrons to move into the conduction band under suitable conditions. Think of a conductor as an open highway where vehicles move freely. An insulator is like a road blocked with a huge barriers. A semiconductor is a controlled gate where traffic can be regulated according to our requirements. In the next, you can see the band gap structure in the diagram below. You can see here the conductors and semiconductors and insulators. In conductors, the energy band gap, the conduction band and valency band are overlapped. Whereas in insulators, there is a huge band gap. It is about 5 electron volts. Whereas in the semiconductors, the energy gap or forbidden gap is lies between insulators and conductors. You can see how the electrons are exciting from the valency band to conduction band and they become free. When the electron is excited from the valency band to conduction band, that creates vacant positions in the valency band. Those vacant positions are referred as holes. So finally, the conduction band is fully occupied with electrons and the valency band is occupied with holes. So in the next slide, we will discuss about the concept of energy band diagrams. To understand why conductors, semiconductors and insulators behave differently, we need to understand the energy band theory. When atoms comes together to form a solid, their individual energy levels combine to form energy band. Two important bonds are valency band and conduction band. The valency band contains electrons involved in bonding. The conduction band contains electrons that are free to move and contributes to the electric conduction. The separation between these two is called energy band gap or forbidden energy gap in the solid materials. Let us compare the three types of materials as shown in the diagram below. First, let us discuss about the conductors, where either the conduction band overlaps the valency band or the conduction band is partially filled. Therefore, the electrons can move easily with very little energy input. So the electron transportation takes place easily, so that it results a good electrical conductivity. So this explains why metals conduct electricity efficiently. Coming to the next part, in the semiconductors process a small band gap. Usually it is less than 2 electron volts. Because the gap is small, thermal energy available at room temperature can excite some of the electrons into the conduction band. Therefore, these excited electrons can contribute to the current flow. Coming to the insulators. The insulators have a large band gap greater than 4 electron volts. The room temperature thermal energy is not sufficient to excite many electrons across this energy gap. As a result, the electrical conductivity remains very low. This simple difference in band gap determines the electrical behavior of materials. Engineers exploit this principle extensively. For example, LED colors depends on the semiconductor band gap. Solar cell conversion converts the sunlight into the electricity by exciting electrons across the band gap. So the rate of conversion of solar energy into electricity by the solar cell is also depends on the band gap of the semiconductor. Similarly, the transistors operate by controlling electrons movement between these two energy bands. Therefore, we can say that the energy band theory is one of the most important concepts in semiconductor physics and electronics. So, in this slide, we will discuss about the concept of electrical conductivity. So, how the electrons transport from the valency band to conduction band, and how the electricity or electric transport takes place. The conductivity tells us about how easily electric current flow through a material. Different materials exhibit enormously different conductivity values. Let us say, if you take a conductor, the conductivity is in the order of 10 power 6 ohms per centimeter. In the same case, if you take the insulator, it is less than 10 power minus 16 ohms per centimeter. So for metals, the conductivity can reach values around a higher level, whereas the insulators are very small. So the semiconductors occupies the middle region between these two extremes. It is between conductors and insulators. But what determines the conductivity? How we can find the conductivity? You can see in the diagram, you can see the flow of electrons, how the electrons are transporting in a material. The conductivity depends primarily on two factors. One is the carrier density, and the second one is mobility of charge carriers. The carrier density refers to the number of charge carriers available in the conductor for conduction. The second carrier mobility. The carrier mobility measures how easily charge carriers move through a material when an electric field is applied. The availability of charge carriers is important. At the same time, the mobility of charge carriers also very important. These two factors affects the electrical conductivity, and we can determine the conductivity using these two factors. Mathematically, the conductivity depends on both carrier concentration and mobility of charge carriers. Even if many carriers are present, but the mobility is very poor, so which results a reduction in electrical conductivity. Similar way, the excellent mobility is not useful if there are very few charge carriers available. Both the things are very much needful and equally important. This is why the semiconductors engineering focuses on controlling both carrier concentration and mobility of charge carriers. For example, doping increases the carrier density. Material purification improves mobility. So the modern semiconductor industries spend billions of dollars in optimizing these properties to produce the faster computer processors and more efficient electronic devices. Understanding the conductivity is crucial because almost every electronic component is designed by controlling carrier density and mobility of charge carriers. In this slide, further emphasizes the relationship between the conductivity, carrier density, and mobility of charge carriers. Let us imagine two highways. The first one is there are many cars but severe traffic congestion. The second one, there is very few cars but the road is completely clear. Neither highways provides optimal transportation. Similarly, electrical conductivity depends on both the number of charge carriers and their mobility. If the carrier density is high but the mobility is poor, that results a limited electrical conductivity. Similarly, if the mobility is excellent but very few carriers exist, still the electrical conductivity is low. The ideal situation occurs when both carrier density and mobility are high. This is exactly what engineers try to achieve in semiconductor devices. For example, in a silicon transistor, doping is used to increase the carrier concentration. The advanced fabrication techniques reduces defects and improves the mobility. As semiconductor technology advances from nanometers to atomic scale, the controlling mobility becomes increasingly important. Today's high performance processors contains billions of transistors where electron transportation must occurs extremely efficient. Therefore, understanding the balance between the carrier density and mobility is essential for designing next generation electronic devices. Whenever you hear the word such as high speed electronics, low power devices, efficient semiconductor materials, remember that the conductivity, carrier density, and mobility of charge carriers are playing a crucial role behind these sense. You can see here the different ranges of this conductivity values are given. If you see the metals, for silver, it is silver, copper, and iron. For all metals, it is 10 power 7 order. Whereas in semiconductors, it is about 10 power minus 4 to 10 power minus 6 order. Whereas in insulators, if you see particularly ceramics like soda lime glass or concrete or aluminum oxide, it is 10 power minus 10 to 10 power minus 13 order. Whereas in polymers, it is in the order of 10 power minus 14 to 10 power minus 16. These ceramics and polymers comes under the category of insulators. Think about the diagram. Here, it is designed to think let us consider a simple question here. Why do, why do we not make computer chips using copper? Though the copper is a conductor which has the more electrical conductivity, we are not using it in computer chips. even though it is better conductor than the silicon. We are using silicon based semiconductors or semiconductor based chips. At first glance, the copper seems like the ideal material because it conducts electricity extremely well. However, there is a problem. The copper conductivity cannot be controlled effectively. That is one thing. The other thing is, once the current starts flowing, it continues to flow freely. That is the problem with the semiconductor conductors. And the other thing is, here we can understand from the diagram, as we mentioned, the availability of charge carriers is one of the important factor. If you see the silicon, in silicon there are 4 electrons available in the outermost orbital. But in the copper, only 1 electron available in the outermost orbital. The valency electron is 1 in copper. There are 4 valency electrons in the silicon. As per our previous discussion, if the electrons, the valency electrons are more, free electrons are more, the electrical conductivity should be more. But here it is quite reverse. The conductivity of copper is far high when compared to the silicon. But the availability of charge carriers in the outermost orbital is high in silicon. On the other hand, the silicon behaves differently by adding impurities. Applying voltage or changing operating conditions, engineers can precisely control the conductivity of the silicon or any kind of semiconductor. This controllability allows silicon to function as a switch, and many other applications also. So in the modern digital electronics relies on billions of tiny switches called transistors. Those all transistors made up of these semiconductor materials. A transistor must turn on or off reliably. So if we cannot control the current, if we cannot control the conductivity of a metal, which cannot be used as a switch. So the conductor cannot perform this switching action effectively because the conductivity cannot be controlled in metals. Semiconductors can, because we can control the current flow in semiconductors. The another question is, why the semiconductor device become more conductive when temperature increases, whereas metals become less conductivity with respect to the temperature. The conductivity of metals decreases with increasing temperature, whereas in semiconductors, the conductivity will be increases with increasing temperature. This opposite behavior is one of the defining characteristic of semiconductors and will be discussed in the subsequent slides. The ability to ask such questions and analyze the underlying physics is what distinguishes an engineer from a technician. A technician cannot think beyond, but the engineer can think and design the new materials. The engineer can discover the new materials for advanced applications. Physics is not about memorizing formulas. It is about understanding why materials behaves the way they do and how we can use those behaviors to create useful technologies that an engineer should understand, and they should be in the position to apply this physics knowledge to innovate new things or new technologies. Keep these questions in mind as we move forward, because they will help you to appreciate the remarkable properties of semiconductors and conclude the classification of semiconductors. And here, the semiconductors behaves differently, like they can behave like insulators at extremely low temperatures, and the conductivity will be increases with increasing temperature. Thank you very much for your kind attention, and once again I welcome you to the exciting learning journey in physics for engineers. Thank you.